Hello everyone, my name is Murali Krishna Reddy Mandalapu. Welcome to the Conf42 Golang conference. Today we will discuss about real-time AI inference at the edge for self-driving cars. Self-driving cars represent one of the most challenging applications of edge computing and AI. Modern autonomous vehicles must process over a gigabyte of sensor data per second from high-resolution cameras, LiDARs, and radar units to make a split-second decision that ensure passenger safety. In this presentation, we will explore how real-time AI inference at the edge enables autonomous vehicles to function safely and efficiently. We'll also examine computational challenges, hardware innovations, and optimization techniques that makes this possible. Welcome. Let's get into the details. First, let's understand the challenge autonomous vehicles pose in terms of the processing requirements. First, the data that it generates is massive. Second, the latency requirements for safe operation of the vehicle on the road is very strict. And then three, the variability of the compute requirements based on the environment the vehicle operates in varies significantly. From the data perspective, autonomous vehicles generate anywhere from 1.4 terabytes to 19 terabytes of raw data per hour from the multiple high-resolution cameras, which operate at 30 to 60 frames per second at full HD resolution, and then LiDARs, which generates 100,000 to 4.5 million points per frame, and radar systems operating at 24 to 77 gigahertz. With all this amount of data, strict latency requirements poses another challenge. Complete perception, decision, and action pipeline must execute within 100 to 300 milliseconds for collision avoidance at highway speeds. Each 10 milliseconds of processing delay translates to approximately 0.3 to 0.5 meters of extra stopping distance, which is very crucial for safe operation of the cars. Next, environmental variability. Computational load can vary by up to 480% between minimal complexity scenarios, which are open highways, and maximum complexity environments like dense urban intersections where vehicles crisscross, humans present, and many more complex scenarios. This requires adaptive computation architectures. Let's understand how edge computing evolved for autonomous cars. First generation repurposed consumer GPUs. Early autonomous prototypes used adapted consumer GPUs delivering up to 12 tera operations per second with significant limitations, namely high power consumption up to 300 watts. This high power posed additional constraints with respect to the thermal management, which required liquid cooling, and also data transfer bottlenecks up to 67% of the processing time. In the second generation, automotive grade accelerators were designed as a purpose-built processors with improved efficiency up to 2 to 4 tera operations per second per watt, with reduced memory traffic by up to 60% through pruning and compression techniques, and also supported reduced precision computing for up to 4x throughput improvement. Let's get into the next level of details on all these techniques. Edge versus cloud computing trade-off. Let's understand the differences and the advantages between edge and cloud computing. Edge computing advantages. It is near instantaneous processing with 5 to 15 milliseconds latency versus up to 500 milliseconds for cloud. Maintains functionality during connectivity interruptions, which may happen up to 38% of the routes. Reduced security vulnerabilities up to 50%. Better privacy protection by keeping sensitive data within the vehicle boundaries. And of course, cloud computing has its own advantages. It is 2 to 3 orders magnitude greater computational throughput. It enables more sophisticated algorithms with higher accuracy it externalizes the power consumption up to 1500 watts for edge processing, as the power is delivered from a grid. There is no limit on the power that it can consume. It is ideal for non-safety critical tasks like high definition map generation, etc. So with that, now let's get into hybrid approach. In the cloud processing, high bandwidth analytics, mapping and fleet learning are used. This is up to 72% of the task. The hybrid processing, where intelligent load balancing with seamless task migration across the platforms is done. The last one is edge processing. This is used primarily for mission critical perception and control systems, which is up to 82% of the processing needs in a autonomous car. The industry has converged on a hybrid architecture that strategically allocates computational workloads between onboard systems and cloud infrastructure. This sophisticated approach delivers almost 100% functional reliability while reducing the vehicle computational requirements by up to 45% compared to pure edge solutions. By leveraging both paradigms' inherent strengths, which is immediacy of the edge processing with scalability of cloud computing, this hybrid framework creates an optimal balance of safety, efficiency, and capabilities while effectively neutralizing the limitations of either approach in its isolation. Let's understand some of the issues or some of the requirements related to various aspects of autonomous driving. First, object detection and classification. This is done mostly at the edge. Performance requirements with the state-of-the-art models, we can achieve up to 87% of precision while operating within the strict latency constraints of up to 50 milliseconds per frame on auto-grade processors. Second, multi-stage processing. In this technique, initial region proposal networks operate at 20 to 30 Hz, followed by more intensive classification networks that process only identified regions of interest, reducing computational requirements by up to 75%. There is one more optimization technique, that is quantization. Quantization, if it is full precision, we use 32 bits, but by quantization, reducing the quantization from 32-bit to 8-bit integer precision, which reduces the memory requirements up to 76% and inference time by up to 3.4 times, with accuracy degradation of only up to 1.8 or maybe 2% compared to the full precision 32-bit parameters. Next, let's understand the lane detection and trajectory planning compute requirements. Lane detection consumes up to 12% of perception budget. Processing camera feeds either in 720p resolution or 1080p resolution to extract the lane markings within 5 to 8 centimeters accuracy at distances up to 80 meters. Multimodal fusion. In this, RGB camera data is combined with LiDAR reflectivity and radar returns to maintain accuracy during adverse weather when visual data quality degrades almost by 60%. Third, trajectory planning. In this task, hardware or the compute requirements evaluates 1500 to 3000 candidate trajectories every 100 milliseconds, which comprises of almost 25% of the computational budget for optimizing the safety, comfort, and efficiency within the strict time constraints or latency constraints we have. Next, let's understand few of the techniques that are used to optimize further on the model itself. Quantization converts high precision 32-bit floating point to an efficient 8-bit integer representation, delivering 4 times weight compression and 2 times actuation compression with minimal accuracy loss up to 1.2%. This is critical for edge deployment. 8-bit operations consume 9 times less energy compared to floating point calculations. Next, pruning technique. In this technique, we systematically eliminate redundant neural network parameters, which are up to 70%. They contribute negligibly to the performance. And then structured pruning techniques yield up to 3.8 times computational efficiency gains while maintaining model integrity. With this, maybe accuracy drops only up to 2% with fine tuning. And then another technique for model optimization is knowledge distillation. In this technique, we use larger teacher models to guide the training of compact and student networks. This technique enables dramatically smaller models, up to 8 times fewer parameters, to capture the essential capabilities of larger architectures while sacrificing only up to 3% accuracy. This is ideal for resource-constrained edge devices. Let's get into some hardware-aware neural architecture search improvements. Automated discovery. Discovers in this optimization, discovers novel network architectures tailored to specific hardware, outperforming handcrafted designs by up to 12% in accuracy while reducing inference latency by 2.3 times, which is very good. Then the second technique is hardware modeling. In this technique, we incorporate detailed models of memory access patterns, operator execution times, and parallelization capabilities of hardware to maximize the hardware utilization. In this, models are aware of the actual underlying hardware and its capabilities to achieve better utilization. Third, sensor fusion optimization. Particularly effective for sensor fusion tasks, reducing inference latency by up to 48% compared to the conventional architecture on auto-grade accelerators. Fourth, attention mechanisms. Discovers efficient attention-based architectures that selectively process high information regions, reducing overall computational requirements by up to 55%. There is also another emerging trend, which is neuromorphic computing. Before understanding neuromorphic computing, let's understand what is event-driven processing. Event-driven processing is, instead of processing data frame by frame, we process data based on an event. This reduces power consumption up to 95% compared to the frame-based approach by allocating resources only when significant changes occur. This also helps temporal advantages, which is microsecond scale temporal resolutions up to 10 microseconds, improves detection latency by 20 to 45 milliseconds for high-speed objects compared to conventional vision systems. This also helps lighting adaptability, maintains consistent detection across illumination ranges from 0.1 luminance to 100,000 luminance, addressing limitations with high dynamic range environments. With this understanding, let's understand what is neuromorphic computing. Neuromorphic computing represents a fundamental departure from conventional architectures, drawing the inspiration from biological neural systems. These systems integrate processing and memory in artificial neuron and synapse structures that mimic their biological counterparts. Prototype neuromorphic processing units can process 50 to 100 million events per second while consuming only 100 to 300 milliwatts of power, representing a 2 orders of magnitude improvement in efficiency compared to GPU-based solutions. Okay, let's summarize. The future. Where are we headed with this? Distributed AI and continuous learning are the future. Distributed AI architectures maintain 85 to 92% of the critical functionality, even with failures in 30% of the processing nodes. Reduce latency by up to 47% for complex perception tasks through better parallelization and reduced data movement. Continuous learning systems. Improve detection accuracy by 15 to 25% in novel environments not represented in initial training data. Employ safety-aware incremental updates that limit parameter changes to only up to 2% per cycle. Federated learning. Vehicles continue to collective intelligence while transmitting only a 0.5% of the data required for centralized approaches. With this, synchronization of every 100 to 500 kilometers provides up to 85% of continuous connectivity benefits, which is a great one. Thank you. With this, I conclude my presentation